hosting the UCMR 5 Small Systems webinar from 11 to 2 p.m. in Teton. To get 4 hours credit, you must stay in the class.
Does someone start the thing off, or I just kick in when it's time? Just going?
7:30.
Okay. Snooze, they lose.
Well, good morning. I'm sure none of you started as early as I did. I drove up from Laramie this morning, left at 4:10, and it took actually all 3 hours to get here. So there is a lot of snow and ice on the roads this morning. Down through Shirley Basin and Medicine Bow area, it is just covered in ice. So drive was fine. You get used to it after I've lived here for 26 years, but it was all good. All right, I'm going to talk about on-site hypochlorite generation, but this presentation is an adaptation of a presentation I gave last year for the American Society of Chemical Engineers of Wyoming, the Wyoming section. And I start off talking about the chemistry of chlorine, and then get into some of the features of on-site generation at the very near the end of the slide. But it's going to give you more of a deep overview of what chlorine is about and the different applications of chlorine and measurements of chlorine. So there's a lot of interesting facets of this. I've been involved with chlorine generation and the measurement of chlorine since about 2004. But I'm an analytical chemist and ion physicist, so I've been doing instrumentation and trace level detection of molecular species since graduate school at Cornell and working for companies in the Bay Area, and then moving to Wyoming in 1998. I moved to Wyoming for a company that's actually showing here called Insitio, and ran their R&D for a number of years before they moved to Colorado. And then I got into the marine applications of chlorine and sensing systems. So I've been in water measurement for a while, and I'm pretty much a seawater treatment and measurement expert. And yes, I'm based in Laramie, Wyoming, where I'm pretty much nowhere near the seawater. So chlorine is the oxidant of interest in biological fouling. I'm going to go through all the different applications. Right now, it's a really big deal in municipal water treatment, wastewater treatment. Typically, you've used different kinds from gaseous to liquid form to on-site generation, but part of the story also cannot exclude bromine. So you hear me talk about bromine as well, because bromine has a lot of similar behaviors that are very attractive, and especially in the marine world, where I have spent most of my career in the water treatment arena. Everything comes down to an equilibrium reaction. So it's kind of early in the morning to hit you with a lot of chemistry, but you're going to get hammered with it right now. Everything is in an equilibrium drive. So chlorine gas is way to the low pH scale. If you look at the bottom axes here, you'll see that's pH from 0 to 11. And when you talk about chlorine, the real biological efficacy of chlorine is the chlorine gas that permeates the membrane of the microbial organisms. But when we want to deploy it, you can do chlorine gas. A lot of places still do use chlorine gas, but that's a hazard, a very big hazard when dealing with it. So liquid chlorine is common. And when you do liquid chlorine, you're the whole way on the right. You're way up high on the pH scale, because you're normally going to buy it in a way where you spend a lot less money transporting it and storing it. So you're going to be in liquid bleach, typically at around 12.5%. And that is pH buffered to be up at around 10. And so if you look at it, you'll be in what's called the hypochlorite ion state. And I'm going to explain this terminology to you because I'm going to use it throughout my entire presentation. So sodium hypochlorite is way to the right side of that scale. And then you deal with hypochlorous acid. So during the past few years, you heard a lot about the coronavirus. Everyone calls your symptoms you get to it the COVID-19, but the coronavirus and viruses and dealing with the treatment of surfaces and reducing the probability of spread of infection, you talk about hypochlorous acid. And the reason you talk about hypochlorous acid is what you do is you keep it in the HOCl state, really close in pH to where it will convert quickly to the chlorine gaseous state. Because if you apply it as a sodium hypochlorite, you're going to have a high pH, and a high pH caustic is really bad for you. It's really bad as an irritant, causes lots of problems. So you dilute it down, bleach down, Clorox bleach, whatever you buy down, you get hypochlorous acid. That's at a very comfortable, near neutral pH, preferably a little bit below neutral, around 6, 6.5. And what it allows it to happen is when you apply it to the surface and then touch it, or a virus ends up on the surface, you can quickly, at the interface of the membrane of the virus, you'll be able to create a pH shift further down that'll create the chlorine gas which will cross the membrane. And that's what causes the devastation to the microbial organisms or any other organisms you're treating to deal why you're using chlorine to begin with and why you're dealing with chlorine. Or bromine. So to the left I show you all the chlorine. You have chlorine gas, hypochlorous acid, sodium hypochlorite. Another way you get it is through calcium hypochlorite, that's referred to as HTH. So that's the solid version of chlorine. Liquid version is sodium hypochlorite liquid, no greater than 12.5% mass volume. And on the bromine side, you got bromine gas, hyperbromous acid, sodium hyperbromate, and you can also buy calcium hypobromate, but they're crazy expensive, that's why you don't hear about them a lot. And there's other toxicities associated with higher level organisms with the bromine gas, the bromine treatments. If you're a seawater treatment person like myself, it's very pertinent that seawater has 18,900 ppm of chloride. Seawater is an infinite reservoir of chlorine to convert into hypochlorous acid or sodium hypochlorite using electrolysis or on-site generation. So it's a great opportunity to just use the water and electricity to disinfect and keep organisms from growing in your cooling lines. But what's interesting in the seawater chemistry, and this is relevant in all other industries, is at the end of the day, you don't need a whole lot of chlorine. You can't actually measure hypochlorous acid and hypochlorite without actually simultaneously measuring hyperbromous acid and hyperbromate. You can't differentiate them in the measurement technologies. And if you go below 65 parts per million in your treatment paradigm, which you do, because you're down usually at half or 1, maybe 2, 3 ppm, all of it in the marine environment is all in bromine. It's hyperbromous acid and hyperbromate, because the chlorine will immediately give up its oxygen and switch over to bromine. So in the marine environments, or any environment where you'll find bromine in your water, and you're treating at low levels, you may actually end up with bromine in your system, and you may end up finding that you don't treat as heavily. And I'm gonna go into all of this in more detail later with slides that show all this. But again, the chemistries are relevant, this pH curve is relevant, and then whether you have chlorine or bromine or a mixture is relevant. So right here is a simple chart of showing your ratios. Like below pH 3, you're gonna have a mixture of chlorine gas and hypochlorous acid. Between pH of 3 to 5, you're pretty much exclusively at hypochlorous acid. Between pH 5 and 10, you're now getting to where you're starting to shift into hypochlorite, and then obviously at 10 and above, you're exclusively sodium hypochlorite. That is what you're buying when you buy bleach, Clorox bleach at the market or at Walmart or a store. That's what you're getting when you buy it in totes or truckloads, when you're getting it guaranteed at anywhere between 10 and 12%. You're getting the high pH shift. To the right is bromine chemistry. Only thing you need to really note there is the pH stabilization chart is just shifted to the right. Bromine has a different stability point and has different interesting applications. So biological activity, this is the name of the game. That's the whole reason we're dealing with this chemistry to begin with. The interesting effects here, again, be chlorine and bromine, and that's why I'm showing this chart, is look at the 90% bacterial reduction here, down to pH 9, I have red boxes. Where you want to get 90% reduction in bacteria, you only need at 100, we'll just do 10 degrees C. You can see there it says 0.05 ppm of bromine versus 1.4. That's showing you the biological efficacy of bromine. It's incredibly high. Bromine is extremely toxic. Many of you may know about, we have there's an aquarium down in Denver, this aquarium at the Rocky Mountains. When I was doing my research for the US Navy, I was all excited because it's very expensive to make surrogate seawater or to buy the salts to make surrogate seawater to do the work I was doing for the Navy in Laramie. And I thought I would go get their water, because they make water all the time. They make 100,000 gallons a day of water down there. So I thought this would be awesome. I called their senior chemist. And I said, yeah, this will be great getting water, and I'm really excited, especially because I need the bromine to do the analyses that I'm doing. And he goes, whoa, we don't do bromine in our water down here in Denver. I was like, oh, interesting. He goes, yeah, you chlorinate, you do anything to create chlorination of water, you kill all the sharks. All the higher level organisms die immediately. So I came to find that they don't chlorinate water in any aquarium at any coast where they have actual seawater exchange. They never chlorinate. And they just do water exchange extremely fast, like they used to do for ballast water treatment, exchange the water, try to flush out the organisms. But bromine is a problem for larger organisms. Bromine is extremely toxic. If you go down to 99% bacterial reduction, you can also see that, again, high pH, you need very, very little efficacy, and temperatures, I guess the upper one was temperature and the bottom one was pH, but now down there you see 0.11 ppm versus 3.4 for chlorine. It is extremely toxic, nevertheless, is said. Because of the pH shift, however, it's great for these wealthy people in the Colorado Rockies who have hot tubs. They will put bromide salts in their hot tubs and spas and then put chlorine generators on them because the bromine doesn't boil off. It actually stays in the hot tub, and so you can have autonomous cleaning consistently, for the once or twice a year they come back to use their vacation houses. So bromine chemistry has got pertinent place, but it's not in normally for human consumption or contact. Anyway, bromine's very, very cool. It does a lot of chemistry. There are rare places that use it in their treatment paradigms, but chlorine is pretty much what everybody uses, and we just go to higher levels of concentration. So as an element, chlorine elementally was discovered back in 1810. I didn't know a lot about this, so I put it just together to look at it. It's a member of the halogen family, obviously. And you don't ever find it uncombined in nature. It's always combined with something. Because of the -1 state, it'll always be found as a salt or a hydrated potassium, magnesium chloride, or a potassium chloride. I mean, pretty much that's where you find it. It's always paired with something, and it's ionic chemistry, so it's a salt. Gaseous chlorine actually is even older. So gaseous chlorine was found in the 700s by an Arabic chemist who I did not know was popularly known as the father of chemistry. But then not much happened after that until the 1700s, when they just started looking at it for treatment in more modern societies, if you will. It was observed that it was soluble in water. It was a bleaching agent. It could be used on vegetation and flowers, and then of course it also became oxides of metals. So chlorine gas is old in terms of knowing it's about, but its effects only became popular since the 1700s, late 1700s. Then we went into liquid chlorine chemistry, and that was in 1805, geologist. And now we get into Faraday's law, so looking about the formation of it, how could you form it? And this led to the electrochemical nature of chlorine and how you can use electricity and look at the amount of charge you put through a solution and look at the mass of chlorine you would form in that solution, which of course would have been sodium hypochlorite. Possibly hypochlorous acid, but it was probably sodium hypochlorite. So hypochlorite has its own CAS number. It's a monovalent, it's an anion. It's a conjugate base of hypochlorous acid, because you saw the equilibrium of the curve earlier. You had hypochlorous acid in the middle. At the high end of the pH, you had the sodium hypochlorite, the OCl negative. In this pure form, OCl negative is very unstable. You won't find it there. So common commercial forms of it are sodium hypochlorite liquid and calcium hypochlorite, or HTH solid. Has anybody here ever worked with HTH at all, reconstituted it into a liquid form? It's nasty, and you really have to have a lot of personal protective gear around you because just the moisture in the air is already converting it into chlorine gas when you're working with it. And at the concentrations you end up making, which are typically about 100,000 parts per million, similar to the liquid, identical to liquid form, it is extremely corrosive on everything. It is a backup to remote places that rely on hypochlorite generators or liquid form. They will often have a couple tons of HTH available in case supply chain, because supply chain is always an issue when you're trying to do things in the North Slope or out in the ocean, because for all practical purposes, those places that we work with are already on the moon. Supporting them is a real difficult scenario, so our equipment and our processes have to be able to handle a downtime or an uncertain event very quickly. Hypochlorous acid became very popular during the coronavirus, because HOCl went down to, say, anywhere from 200 ppm down to maybe 50 ppm. Very low. If you have very low salinity as you make it, you can just spray it on a surface, a hard, non-porous surface, and it'll kill 99.9999% of any coronavirus, rhinovirus, norovirus that's on that surface immediately, within 10 seconds. So it became very popular to go through and use sprayers and spray walls, spray trucks, spray classrooms. More commonly, you will find that the big chemical manufacturers are better at selling more complex molecules that are persistent, unfortunately, to treat surfaces. So you'll find the big chemical manufacturers do a lot of good jobs of marketing and making sprayers, but there'll be a lot of quants out there and persistent compounds that they use to treat surfaces rather than hypochlorous acid, which is really one of the safest ways to do it, because as soon as it decomposes, it's salt. All that's left is salt. You don't have a persistent compound, and it can be washed away, wiped away. It doesn't create any long-term persistence. But the quaternary compounds they use and all the other complex organics might have a long-term impact and impacts to different aged people who are exposed to it. Let's see here. Then hyperbromite has a different CAS number and shares a lot of commonalities, as you would see with regard to the chlorine chemistry. It's not particularly popular because, one, it's cost. It's really expensive because bromine is much less available in terms of nature. So separate it out is very expensive, but then it's extremely high microbial activity, makes it a bit tough to handle, if you will, because it also has effects to higher level organisms. All right, I threw in chlorine dioxide since the last time I did this presentation, because when you talk about on-site generation, people are also starting to think chlorine dioxide is an on-site generation of chlorine. Okay, part of that statement's true. It is on-site generation of chlorine dioxide, but it is not an on-site generation of chlorine. Because chlorine dioxide is a neutral molecule, it does not actually react with water to form sodium hypochlorite or hypochlorous acid. Chlorine dioxide is an extreme, its capability is that it really wants to steal electrons from something. And it can steal a lot of electrons. And so it reacts differently. It reacts by creating radicalization of the membranes or the organics that's attached to it, and destroys other things. It's has a high propensity to form disinfection byproducts, and you have to really be careful with the kind of water you treat with it. Now, there are water treatment systems out there that rely on using some kinds of chloramines that's part of their treatment process, where it's not considered a disinfectant byproduct or something you want to have to treat the water. Chlorine dioxide is good at that. But it is not the same chemistry that goes on. It does not form chlorine gas at a membrane interface and cross the membrane interface to wreak radical reaction destruction on the microbials. It is just a indiscriminate molecule that wants to suck electrons out of the system. So it's different in its behavior. So I won't talk a lot about chlorine dioxide, but I will mention again later when I talk about the on-site generation, things that are pros and cons about them, if you will. But you can generate it on site. You can generate it from very nasty other chemicals on site. So is it technically better than using chlorine gas and having bulk, concentrated chlorine around? That's up to your processes to determine that. Okay, so chlorine, hypochlorous acid, and hypochlorite. They're both disinfectants, and they exist in equilibrium. So I'm reflecting back on what I just mentioned here. They're just an equilibrium reaction. So if someone wants to go sell you hypochlorous acid, and you're like, well, I really have to have sodium hypochlorite. Well, all you gotta do is shift the pH, a little bit of muriatic acid or a little bit of sodium hydroxide. Moving that pH around, you can get whatever you want. They're all one and the same, and typically you would buy it for your operations. You would buy it as bulk chemical in a truck or in a tote. That's sodium hypochlorite. And as you dilute it into your processed water, the pH is going to shift downward. And as that pH shifts downward, it's going to go into the hypochlorous acid phase. And if you shift it even further down, which you won't, because drinking water is typically going to stop right in that 7 range. That is all you need then for when it comes in contact with the membrane surface. At that surface, it'll shift itself down and create the gaseous interface. That's kind of what I just said across all those other things right there. And this is just a bigger version of the graph, in case you can see it. And the typical range of products I have listed here, you can see where I spent most of my career in the seawater chemistry. So I typically work with seawater that's around that 8 range, 7.8 to 8.2. And when you run it through an on-site generator, a sodium hypochlorite generator, it will shift it up just a hair to the 8.5 to the 9 range. If you do start with on-site generation of hypochlorous acid, you'll start with a brine that's down in just below pH 2, and when you're done running it through the on-site generator, you will shift it upwards quite heavily so that you don't form chlorine gas while you're running your on-site generator to form hypochlorous acid. We actually, this past year, got an EPA certification on our hypochlorous acid generator version of our sodium hypochlorite generators. So we actually do have an EPA certification for the pesticide, which is what they classify it as, to make that. And so now we have a certification and proof of efficacy. At the top, I threw out something else here. I live in a world of total residual oxidant. So when I'm looking at a water system for treatment efficacy or treatment capacity, and especially productive efficiency of an on-site generator, I really need to know how much active chlorine do I have. So in the aqueous form, we have to the right sodium hypochlorite, and to the left hypochlorous acid. When we're running a generator, we have neither of those species, so they're in an exact equilibrium, but you need to measure the total residual oxidant because it's the combined reservoir of the OCl negative and the OCl paired with hydrogen that creates your poise, or the ability of the water to treat as you've treated the water initially and as it goes downstream, as it goes down to, reacts with exposed to metal and exposed to organism, exposed to organics. In water treatment, you want to have a residual when it comes out the tap, not a lot, but just a little, so your total residual when you generate it is going to lead to what's that total capacity. And I'm aware a lot of municipal water treatment places, they typically look at FAC, free available chlorine. And that's the number of interest, and everyone's all excited about that. Well, it turns out when you're looking at free available chlorine, you're often using a membrane amperometric sensor or a DPD type sensor where it's an online colorimetry, or you're taking a sample, doing a grab sample, and I talk about those later in the measurement section. The relationship between them is just pH. Free available chlorine is the HOCl side of that. That's just looking at HOCl. You're looking at the free available chlorine means that form of the liquid chlorine, the hypochlorous acid, that's immediately going to convert to chlorine gas when it approaches an organism. The total residual is, it's the OCl negative. So when you first buy bleach and you measure FAC, you're pretty much got 0 FAC in your pure bleach, because it's all NaOCl or whatever other possible cation compared with the OCl. And the two are just related by a pH shift. So as long as you're measuring TRO, total residual oxidant, and pH, you can calculate your FAC. Or you can measure FAC and then throw a pH at it and then figure out your total residual. But what matters in terms of what you're dosing at the end of the day instrumentally is total residual, because all of it will shift down over time in all your treatment applications. All of it's going to shift down to HOCl as you use it, because that's the nature of equilibrium. Think back to, if you go way back to high school chemistry, there's reactions that showed equilibrium, and then get into college chemistry, it's always equilibrium. As you pull one away, the other one shifts over and forms an equilibrium. So the more I suck out the HOCl, the more OCl will convert over. And the more I form chlorine gas, I'll use all of that total. But pH. So in seawater at approximately pH 8 plus or minus 0.2 pH units, FAC is about 85% of TRO. And when I first started doing some work for some of the oil companies that have seawater treatment systems, like, how do you know that? I was like, because seawater is at the same pH. That's why it's the same in San Diego as it is up in the Bering Strait, as it is on the Atlantic Ocean. It's same pH, same relationship. So it's not magic, it's just chemistry. Ergo chemistry, electrochemistry. If you want to tune out, this is a great time to do it, because electrochemistry is, as far as I'm concerned, the least scientific of all the possible arts of science. It is mostly, in my mind, black magic. In graduate school, I took electrochemistry. I absolutely despised it. I went into mass spectrometry, which was all ion physics and controls of electromagnetic fields, and everything did exactly what theory said. In electrochemistry, nothing worked. And then I called my professor back there after I took over electrochlor and said, I'm now doing electrochemistry. He just got a kick out because he knew how much I hated it. So electrochemistry is a challenge because you deal with this thing called reduction potentials. E super not there, or E reduction. The whole world is expressed in half reactions, and this is where you're going to see some nice little chemistry here. The greater the standard reduction potential, and everything is, it's kind of like discrimination to those poor oxidants, because everything is positive in the reduction side, but discriminating and negative to be an oxidant. But everything is expressed one way. You have to be a reduction potential. So, in other words, reactants are better oxidizing agents. They will take electrons away from the environment. So in fluorine, we have fluorine gas. If anybody's worked around fluorine, I've worked with fluorine lasers that use fluorine in grad school. And just a small leak out your exhaust hood will kill all the pigeons in like several city blocks. Birds are particularly unable to tolerate fluorine gas. And I will tell you, it burns your lungs like crazy. I had some leaks, and it was not a good thing. But in grad school, you're expendable, so you just deal with it, go in, fix it. You don't call anybody in facilities, because then they'll come reprimand you. But fluorine is a very strong oxidizing agent. It's an oxidant because it'll take electrons away from everywhere. It's on the left side of the periodic table there, and so it has a very high positive reduction potential. And then you go all the way down to lithium, which is the opposite side of the equation. So fluorine reduces more easily. It has a more positive reduction potential, and therefore it is a good oxidizing agent. Lithium would rather undergo oxidation, has a more negative reduction potential, and hence it is a good reducing agent. This is just annoying. No matter, I've been in chemistry a long time, 30, 40, 35 years or so. I still can't memorize this hardly well. It's just something I memorize and I forget about. But more positive, more easily reduced, and it's an oxidant. More negative, you just have to have one or the other, and this is the whole basis of the chemistry. However, what's more interesting is the chlorine oxides and their stability. So looking at the reduction potentials in the top of this chart, 0.89, 0.78, 0.68, 0.56, you'll see hypochlorite is right there at 0.89, and because it's, it is, let's see here, more stable. So the most stable is going to have the lower reduction potential, and the less stable is going to have a higher reduction potential. So you can see hypochlorite really wants to react with something. So it is a good oxidizer. It wants to be reduced. Perchlorate is becoming a little bit more stable, and now you're into rocket fuel. So perchlorates are used in rocket fuel. The solid rocket fuel boosters that were on the space shuttle program for all those years were perchlorate based. Morton Thiokol was really good at it, and you all might have seen the video when one of the Morton Thiokol plants blew up in Utah one time. They were doing a test and the whole plant blew up, just disappeared. It was pretty impressive. But perchlorate is still extremely reactive, and if you look at the lower table, when you have perchlorate paired with a hydrogen, so you stabilize it, you would think by having it no longer in a cationic form, you have it in a neutral molecular form, it is extremely explosive. So all these chlorates are not healthy, and you don't want chlorates, ClO3s, you don't want ClO4s in your drinking water. They are associated with carcinogenic behavior. You don't want chlorates at all, and interestingly enough, chlorine dioxide is formed through handling sodium chlorite. So the precursor to the on-site generation of chlorine dioxide is an extremely volatile explosive. Meaning if you mix it wrong or have a leak of the precursor, which you're acidifying, so you're starting with sodium chlorate and an acid, a strong acid, and you mix them and you make something that is chlorine dioxide, those two by themselves are nasty to begin with, and then you end up with another heavily high oxidant. But anyway, sodium hypochlorite here, it's fairly stable. It's got a high, it's fairly unstable. It wants to react, it wants to break down. So, but the byproduct, disinfectant byproducts that can form, chlorates, chlorides, perchlorates, not so good. And that is something sodium hypochlorite on-site generators generate, and I've been through a lot of challenges with other PhD ion physicists and PhD biologists and chemists that have declared that on-site generation produced chlorates. They've shut down our chlorinators, they've done studies showing it generates it. They've asked me to come on site. I have looked at their studies after heavy review. I have then collected on-site data, and I've proved all of them wrong. That the amount of chlorates formed in an on-site generation are lower, below detection limits in the parts per billion range. So they are not causing problems, but HTH does create a little bit more, but on-site generation is extremely safe. It produces a really good, stable product. And here are the chemistry of how you do electrolytic generation. I don't think I want to walk through all of this to you, but we'll say that there's an anode and a cathode, traditional electrochemistry, batteries, car batteries. At the anode is where we form the chlorine gas momentarily before it reacts with the water and forms sodium hypochlorite or hypochlorous acid. That's the anodic side. The anodic side has what we call the coatings, the catalytic coatings, the mixed metal oxides, the very expensive ruthenium and iridium oxides are on the anode. That's what leads to a lot of the CapEx costs. Your CapEx cost is not due to all the titanium that we use in our electrochemical cells. It is due to the very trace amounts of iridium and ruthenium we put on the cell coatings. That is crazy expensive, especially with electric vehicles having taken a stronger run for it, and China is one of the main places you can get these rare earth metals, and as a result of them making all these batteries, the run on iridium and ruthenium has just been crazy in the past 3 years, about 1,000% fold increase in the cost. So it's been crazy. The U.S. has got to get a supply chain stability in that. That would be nice. But that's where a lot of the cost is. That's where a lot of the fixed cost is in your CapEx for on-site generation is the anodic coating, and the anodic coating, you want it to last several years. You don't want to be replacing that all the time. The cathode is nothing interesting, just usually plain titanium, pure, commercially pure titanium, either from China or Russia, so you can probably guess now where we're getting it from exclusively. And nothing exciting happens there except that's where your hydrogen comes from. So during the time you're running the water through it, your anode's at about pH 2, 0 to 2, and a few millimeters away is your cathode, and that's at pH 11, 11 to 12. And so you got these two things separated by incredibly small distances with two entirely different chemical reactions occurring. That at the end of the day, you waste hydrogen gas, and you get out of it, you have sodium hypochlorite. And the lower reaction is the same thing happens with bromine. Bromine is really not fair in the sandbox, because whenever an NaOCl is formed, the bromine steps in, knocks the Cl off, and takes it. And so if you have any bromine in your system, it'll completely go to the maximum level of bromine that it has, so in seawater 65 ppm. So we generate typically in seawater 2,000 milligrams per liter of equivalent chlorine. And of that, 65 of it will be bromine, and the rest of it will be chlorine. And the bromine will always be oxidized. The chemistry is simple, pretty straightforward. Something else happens when you're doing it, not so much in the municipal water side, because in the municipal water you have very low levels of hardness, magnesium and calcium. And if you soften the water before you go into an on-site generator, you will have even less calcium and magnesium. And that's the only maintenance part of on-site generation, is to remove the inorganic scale, what we call the calcium carbonates, the magnesium carbonates, magnesium hydroxides, remove them from the cathode. Because as that builds up, it creates an insulating barrier. And so the electrical potential to still run the reaction, because in order to drive the current through your cell, you have to have voltage. The voltage is your driving force. As you create an insulating layer across your cathode, you have to increase the voltage. And power equals current times voltage. So you're running the same current at all times, but the voltage required to generate that stoichiometric amount of total residual chlorine keeps taking more and more voltage, and eventually you're going to be burning too much power. Power is a cost. So your on-site generation in a landlocked environment like Wyoming, we need to use salt and electricity. Water typically is pretty much not an expensive commodity. It's pretty free at the end of the day. So the electricity and the salt remains the same because you're still generating the same amount because you're running the same amount of current, but your voltage keeps climbing as you scale the cathode. And as the voltage keeps climbing, your power keeps climbing. As your power keeps climbing, the kilowatt hours are ringing up. And there's your cost. There's a cost driver there. So to remove that in the case of a marine environment, so our cells, what we've done at Electrocore, we were designed around marine treatment. We've been running power plants and water treatment systems across the world, and we run in seawater. And seawater has a ton of calcium and magnesium. It makes groundwater look pure. So we do have to acid wash. We acid wash typically every 200 to 400 hours. We'll shut down for an hour, and then we'll run a low pH solution through the cells and pull off all the base, the bases of the calcium and magnesium hydroxides and oxide carbonates. So we do that once a week. It's just an SOP. In brining salt saturation systems for municipal water, you don't do it very often at all, because you're not building that film up near as fast, because you're at orders of magnitude less calcium, less magnesium. But that's one of the sole maintenance issues with dealing with on-site generation. The hydrogen gas, people get all excited about that. Oh baby, can I put that in my car? Can I do something with it? Well, I'm like, the energy density of hydrogen at atmospheric pressure is not really exciting. We do generate a lot, so we generate 8 liters per minute per kilogram per hour. Sorry, I tried to start turning my kilograms per hour into pounds per day or something more relevant to the imperial units that we use in the United States, but I spent the past several years doing ballast water treatment systems for ships, and all of that is IEC driven and it's all metric driven. So I spent several years trying to get out of the English system, and I did so good at it now that I actually can hardly think in terms of pounds anymore. So last night I was trying to convert a lot of this back, and I missed this one here. So later out you'll see what a kilogram per hour equates to. But it's a lot of pounds per day. It's a lot of pounds per day, because it's pretty impressive. But 8 liters per minute of hydrogen is a lot of hydrogen. We do vent it out the top. We do it differently than our competitors' technologies, who were based on municipal water treatment. We were based on marine treatment, so we have a different way we deal with the hydrogen. But nevertheless, it just goes out the vent. Even on the ships that we're on, they don't even direct it back into the intake of the ship. It's just not worth their time. It's not a lot of energy density. So we deal with it. We have sensors for it. Most places just vent into the atmosphere, and it's a day. But one comment here is, in ballast water treatment, however, we cannot leave it in the water stream, because in a ballast tank, it has a head, and in that head it's a confined space, and if that head were to spark, it will cause the tank to burp pretty heavily, and it will cause a problem for the vessel. So we have developed our own inline separators for hydrogen, and we can remove 99.5% of it, and that leaves it's still a safe situation for the ship's ballast tanks. And we had to go through a lot of hurdles to be a ballast water treatment manufacturer. Okay, so the predominant reason, two primary uses of chlorine on-site generation are for biological biofouling control, and the other one is for potable water. You want to reduce biofouling, and you want to make the water safe. Get rid of the viruses and organisms that make people sick. I'm going to start with the biological fouling, because that's how electrochlor got started back in 2001. We use seawater, and on-site generation is way less expensive than doing dry calcium hypochlorite or using liquid sodium hypochlorite. So the way everybody wanted to go is on-site generation. And again, here I mentioned a chlorine dioxide. While it is an on-site generated source of a chlorine compound, it is a different type of reaction. It's a different beast in how it's treated. So our historical business, and this is actually, I took over the original electrochlor in 2017 and moved it to Wyoming in January 2017. And I was remodeling our buildings. We were trying to get started. And I actually ran into Governor Meade at a Home Depot in Cheyenne. This is something I don't think happens in any other state. And I started talking to him, and I don't know why we were talking. We were talking. I mentioned what we were doing, and he said he wanted to come see what we were doing. And I didn't have a building done yet. And I was like, I was still working in a garage at my house. And I'm very sarcastic with government people. I was like, yeah, right, you'll come by. I said, you give me your card, I'll call, and nothing's ever gonna happen. And he taunted me and said, no, we will call you back, and I will see to it. And so I thought, he seemed pretty sincere, so I did. And even though it took a while before he came over and visited, his office administrators called me every time there was a delay, and were very clear that they were never to not let me in to know when he was coming because of my taunting, that he wouldn't show up. So he came to our facility, and that's me giving a lecture to Governor Meade there sitting on the left with his entourage of other people. But he came over, and what I explained to him is what we do predominantly up until we started entering the municipal waters. We've done the reduction and elimination of biofouling and heat exchangers. So in seawater, power plants, they all produce a lot of heat, and they gotta cool their recirculating water back down, and they use open seawater exchange. Seawater comes right in out of the Mediterranean or the Gulf of Mexico, goes through the heat exchangers and goes back out. So they pull in water nearby and then they discharge it a mile or so out in free ocean, in the free sea. That is where we have humongous chlorinators. That has been our claim to fame since 2001. Big systems. I mean, you think you're treating municipal water at 52 million gallons a day. That's interesting. We're treating 10 times that, 100 times that in seawater cooling plants all over the world. And these are huge systems. And the nice part about this application is, for instance, in Algeria, one of my favorite places, sort of sarcastically, but they have a great chlorinator there. But when they don't maintain the chlorinator, they lose power in the capital city. Yeah.
I got a question for you. So, when you guys were bringing the seawater in to use it to cool things down, were you then creating enough condensation and steam to make actual physical drinking water? Was it like a multi-purpose thing? You couldn't have enough steam generation that would produce actual physical drinking water when cooling it down and make it like a dual portion deal?
None of the power plants that we've been exposed to are even thinking that far ahead in terms of making potable water, but certainly they could, but no, we're just.
How much would it be if that sounds like a very large volume of seawater that they were.
But it's purely for cooling, and it never gets boiled because the boilers are a secondary loop. So you got to remember the boilers are a pressurized steam loop independent of the seawater, which is bringing the waste steam back down to a lower temperature before it's reheated again. So there's an open loop with the seawater cooling.
So the seawater was never really physically turning to steam?
Never was, never is.
Okay.
No, it's just getting hotter by about 20 degrees centigrade.
If they could get that and be that close to produce drinking water, they'd have something there.
That's an interesting thought, but these power plants are designed just to keep the electricity running. And they're pretty sensitive about the biological fouling because biofouling will crash the whole plant. But interesting thoughts there with regard to generation of potable water. But I've not heard that anybody doing that.
It just sounds like a large volume
Yeah.
of water that you're utilizing.
Well, so at the North Slope, a quick aside here, we have a very large chlorinator in the North Slope, and it's right on the Arctic Ocean, north of Prudhoe Bay, even further north. And I thought, great, we're supplying a chlorinator. We're going to be dealing with cold seawater. We have to have electrochemical cells that have to be a special catalytic coating to deal with the oxygen formation of cold seawater. And they're like, oh, no, it's not cold. I'm like, what do you mean? It's all 70 degrees C, or 70 degrees Fahrenheit. Sorry, I think Fahrenheit now. I was like, well, how did that happen? He goes, well, we have so much waste gas coming out of the fields on the North Slope that all the dog gas has nowhere to go. They burn all of it to their greatest extent that they run on-site electrical generators. They heat the seawater up literally in a matter of 5 feet. They're running 32 million barrels a day. All of that water is heated to 70 from 0 degrees C plus or minus 2 degrees. It's heated immediately to 70 degrees C, Fahrenheit, 70 degrees Fahrenheit. And then we're chlorinating it, and then we're dechlorinating it, and then passivating it, and then doing all kinds of other stuff. And they had the wise idea, this is an interesting story, they thought for a year they turned off the chlorinator because someone declared that we were making perchlorates. So in their wisdom, Bartlesville, Oklahoma said, we're shutting down the chlorinator, we are going to do something else, and we're not gonna, and they also were misreading their TRO readings that they were doing by hand, and they stopped chlorinating effectively, and they created a whole new biologically resistive strain of organisms in their surge tanks that could not be treated with glutaraldehyde. And so when I went up there and I started doing all the biology and tracing the biology, because I'm a pretty versatile chemist, I chased the biology down. I said, here's where your problem is. And they were just like, you gotta be kidding. I'm like, no, it's in this 10,000 gallon surge drum, both of them. And you're creating more organisms. We came in, we killed everything, just like we said we would, but went into the surge drum, passivated, neutralized, and chlorinated. It came out teeming with more biological life than what came in from the raw ocean water. And all of it was resistant to glutaraldehyde and chlorine. And it was being distributed through hundreds of miles of carbon steel pipe. And they were getting corrosion rates sky high and all kinds of problems. At any rate, I then served in their team for a little while and they got all straightened out. But it took a lot of effort to upset the pylons that hold this plant above the tundra to shut it down, one of those surge drums, so that they could get people in there and literally hand scrape it and then change their whole chlorination paradigm again. And then a year later, they did something else wrong and I had to go back up and fix that too. But The problem when you have too many chemists and physicists and biologists on a committee versus when I just come up there and just flat out just go, here's what your problem is, deal with it. But seawater treatment is really exciting, it's cool, it's really great for us in Laramie because every time I go on a business trip, I'm going somewhere really warm and nice, except to the North Slope. But I love the North Slope. The other thing we've done a lot of in the past several years is sanitization of processed water in fishing boats. So on all the fishing boats, let me watch my time here. On all the fishing boats, they have a processing deck. And so we actually would take a slipstream of their water and chlorinate that through one small little electrochemical cell, and all their water coming out, flooding that entire deck, has got a little bit of chlorine in it, which is safe for drinking. We got into invasive species by doing ballast water treatment, and so now we're an OEM. So there's one of the major manufacturers of ballast water treatment systems actually buys their technology from us in Laramie. So we actually design and build their systems, and they're privately labeled for them. And we export those all to China or the Middle East where they're installed on ships. And so now we're in ships all over the world doing ballast water treatment. And this gets us into the reliability and the requirements for having a system that does not fail, because a ship is the last place in the world you want to have a failure and deal with service, support, and getting spare parts to it. So it's been a really good exercise. We've done really well at it. And now we are getting into wastewater treatment, environmental remediation, and then disinfection. So I kind of just went through this whole slide really fast there. This is my fun place. I just, this picture of where I like to go the most, which is up in the North Slope, right out there on the sea. And this is that chlorinator right there on the North Slope. We actually replaced a system that was the size of, say, 2 Ram trucks and weighed 3,200 pounds with a system that was smaller than a Volkswagen Jetta and only weighed 800 pounds. That was the big change in the technology going forward. On ship-based chlorinators, this is an offshore platform owned by Oceanics. This is in Singapore. The really cool thing about this was the chlorinator on the left is up 132 feet above where our supply water comes from and where we dose to. That creates an incredible amount of water hammers and a lot of interesting anti-siphon issues that go into effect here when you're trying to treat all that water, because all the treatment's down under the water level. Really neat hydraulics that we had to deal with. But it all ended up working very well, and they actually bought more of them from us. Okay, so I'm gonna this is the generation of chlorine. So the benefits of on-site generation. Transporting, you don't have to transport hazardous material. You are not gonna store hazardous material. You're not gonna handle hazardous material. Now, one of the interesting things is the EPA threshold for hazardous material in dealing with hypochlorite or hypochlorous acid is anything less than 1%, 10,000 ppm is safe. There is no restrictions with it whatsoever. You can splash it on you, wash on it. It doesn't really hurt you. It's not that much. Go ahead.
So that 1%, as we know, that's normally how we, is equal to 10,000 parts per million?
That's correct.
Okay.
That's correct. That is the conversion. Believe me, I have cheat tables on all my spreadsheets because percent is a weird number to deal with when it's dealing with ppm. But yeah, 10,000 ppm is 1%. And our systems put out anywhere from 0.2 to 0.4%. So 2,000 to 4,000 ppm. You will find in on-site generation, a lot of systems do 0.8%. And if you're interested in why we don't do 0.8%, feel free to talk to me afterwards. But there's a reason why we're not doing it. We don't want this, we're not a Me-Too company. We're a marine company that are gonna make something that is reliable that we make as reliable on shore as we do in the marine environment. So, no equipment to dispense corrosive material, no PPE, spill prevention, and you're not shipping and transporting a degradable dense product at the end of the day. Because the higher the concentration, the faster the degradation rate is. This is a ballast water treatment system showing where our systems are usually in the backside and the safe areas where our chlorine generators are, and then we dose up into the unsafe side of some of the bigger ships. It's a really cool situation to be in. And we make all of these are versions of what we make. The cool part about the way we do it is we actually paid for all the design and development of our customers' ballast water treatment systems, so we can use any part of that design in any of our shore-based systems. We just can't sell into the ballast water treatment market against them, but we own all the designs, and so we own all that expertise and all the engineering. And so we ship full 3D models of everything to all the integrators and the ship manufacturers and ship owners, so they can drop the models into their ship and then design around and install them. So we do chlorinators and dechlorinators and dosing systems and measurement systems for all these ships. PIDs are pretty fun to deal with. And now we'll get into what we do. We have a multi-pass electrochemical cell for our on-site generation. That's not different than anybody else. Everybody has to have an anode and a cathode. In our case up there, the anodes are red and the cathodes are black. And the difference between ours is our competitors are parallel plates. So they have I'll show you a cell in a few slides here. But basically water comes in and then it picks and chooses what slide it's gonna go through, it just goes through. As a result of that though, you don't control the hydrology or the Reynolds numbers of any particular pair of plates. So one could foul and the other ones will make up for the flow rate. You know, one could scale up or fail in some capacity. Ours can't. The water flows through these concentric tubes. The same water flows through all of them. So we have control of the Reynolds number, and we have control of the fouling rates, if you will. So as scale accumulates, we can shed it. We could burst the cell to a higher flow rate and shed scale rather than doing acid washing, or we could stop and do acid washing. But we're always guaranteed to flush all of our electrode, anode, cathode areas. Once you have a cell that's a parallel plate cell, you can never actually get in there and fix the cell that's gone bad. That fraction of the cell that's gone bad is going to stay bad unless you really do a deep soak and take a lot of time or take it apart. The other thing going for us is these cells are 100% titanium. They are solid welded titanium. They just have one set of sealing surfaces way on the far right there. There's a gasket setup made of UHMW, high density polyethylene cross-linked, and then Viton gaskets. That's the only place there could possibly be a leak, and we never leak there. I mean, we can if you overpressure the cell, you know, because it's a pretty large diameter. But that is the extent of it, and we have a cold water anode coatings and we have warm water anode coatings. And we work very hard to keep with our vendors and who we choose to do our coatings to hit whatever warranty performance requirements we're looking at for the application and price points. So I won't go through all of this detail, but we have all the spec sheets and data sheets on all of our electrochemical cells. We have cells that run anywhere from, this is what we call 4 kilogram per hour cell. So I did convert it to pounds per day, 211 pounds per day for one cell. One electrochemical cell can do 211 pounds per day. You might find in the Chlortec and other systems out there, they have cells designed around 20 pounds per day. Each cell's 20 pounds per day or is 40 pounds per day. Well, our base cell that we use in the marine market is 200 pounds per day for one cell. But that cell takes 4,000 amps of current. It looks pretty hazardous, but it only is running at 3.2 volts, so you can walk up and touch it. It's like a big welder. Big monster cables, and we have the gaskets protruding, so you can't actually drop a screwdriver across the place there, so it welds it shut. But it's pretty safe. You know, it's non-hazardous to touch or be around. Just a lot of current, but not a lot of potential.
Would you say the voltage was?
The voltage typically to run one of these is 3.2 to 4.2 volts DC. So only when you start stacking a whole bunch of them in series, electrically in series, then you're getting up to 60 volts or 80 volts or 100 volts DC. But it's all 4,000 amps flowing through every cell, these big ones. These are not the cells we would typically use in a municipal drinking water market because these are too big. That is all your eggs in one basket. And usually in a water environment like this, you want to have multiple flow trains, you want to have redundancies. You would not use one of these big cells. So we actually have a smaller cell, 2 kilogram per hour cell, which I took out of the slide set here. But these are the size comparisons of some different cells. The 1 kilogram per hour cell, which is on fishing boats, is 53 pounds per day of chlorine, effective chlorine. Up to a 2K cell, which is 106 pounds per day, to 211 pounds per day. That's the market we're in. We now do have a half K cell, which is by itself, it's about 25 pounds per day and can go lower. So we have different technologies now as we've been entering into the municipal water market. This is a traditional cell, which we OEM to another company for them, and it's the parallel plate design. You know, it's got some housing, a superstructure, a bunch of really close spaced parallel plates, but it's really hard to deal with the fact that water slipstreams around everywhere. You have no idea what's going on in the middle, but you do have lower current, but higher voltage. So these cells work in a paradigm of power is the same no matter what. You can't get around, it takes the same amount of power to generate the same amount of chlorine no matter whose technology you use. But this is a designed to be low current, high voltage. Ours are designed for high current, low voltage. Then the other thing that comes into play is whether you go to 0.2%, 0.4%, or 0.8%. The higher you go in the concentration, the more scavenging losses you have in heating the water up. So they start losing more power due to heating water. There's a variety of games here. So if you want to get into this market yourself because you really think this is easy, write all those variables down and go play with them. And they're all nonlinear. And try to solve something that the industry has missed over the past 100 years. There's a lot of interesting things that go on. So even current density is something we also have with our cells, and what you want to get with any cell technology, even current density gets long life. If you don't have even current density, you run into lots of problems, but our tubular electrochemical cells deal with that. The nested tubes result in less scale buildup, more control of that scale, more control into fluid dynamics, which can be in your favor. And we can run our electrochemical cells in series and parallel configurations to generate what I call standard output is 2,000 parts per million or less. Now our systems run PID controlled, so you can take our system and have it generate 1 kilogram an hour, half a kilogram an hour, 1/10 of a kilogram per hour, or pounds per day, whatever. You can just dial in what you want. We don't run full bore on off. A lot of systems out there designed for the municipal market are on off, so you have to have big storage tanks. Yes, back there.
Well, how are the ships then? Because how are they adding and taking away voltage out of the ships?
We supply 480, so we use 3-phase rectifiers, 480 volts AC, 3-phase, and we rectify that to DC, and then they control the DC current.
So they're running off of a generator, I think.
They have, right, they run gen sets. Yeah, they run gen sets. So they'll, in fact, our system draws so little power, what they look at is how much diesel do they need to burn to treat their ballast tanks. So we work with them in terms of gallons of diesel. At any rate, so we're PID controlled, so you can take any system, and we have a turn down ratio of about 100 to 1. So it may produce 1 kilogram per hour, but it could produce much less than that. Or our bigger systems produce 100 kilograms per hour. They can produce much less than that. There's a rendering of a system we actually make today. They're just prettier than when I take pictures of them in our shop. But this one here does 211 pounds per day. That's all the bigger it is. I mean, it's barely, 5 feet wide, 3.5 feet deep, 4 feet tall. They're not very big. And that one can do municipal water, 211 pounds per day at 0.4%. We have all the general arrangement drawings of all of our systems. This is a larger scale system that does 846 pounds per day. And again, it's not actually much bigger, just taller. And then the rectifiers are shown there as well. And that only has 4 electrochemical cells in it. No, that one has 8 electrochemical cells in it, 8 2K cells. And these are the really big ones we use for, this is a 4 kilogram per hour cell basis, so 1693. It's only as wide as this table, a little bit deeper, about this tall. And that will do 1,693 pounds per day of chlorine, and that one's designed for marine markets, treating power plants. And we've sold lots of those. So when it comes to measurement, so how much time do I have? I have like 3 more minutes left. So interrupt me if you have more questions, but the measurement techniques are gravimetric is your most common, most precise measures. You're using in the lab, burettes to do gravimetric measurements. Your digital titrators like from Hach are similarly accurate. They're the best ways to go. I use a lot of these handheld optical meters, and the problem with all these meters is you got to deal with your water turbidity when you first take your measurement. You got to be very careful that your water is clear and pretty. When I went to the North Slope, because of their rapid treatment of the water, their water was effervescent. They actually ended up creating a lot of trapped air in their water. So when they shut down the chlorinator and backed it off, it's because they were measuring turbidity, not color. And they didn't know that for over a year. And so you have to understand your water quality, your water chemistry, and your sampling protocols in order to make these work. We sell a ton of these online optical measurements, but these are a real difficulty because the chemical reagents that they consume are dangerous goods in shipping. They have a waste stream, which you have to deal with as well. And they're now going to be replaced with this online amperometric, but these are solid state, not your membrane-based sensors that you use today that are dependent upon pH because they're measuring free available chlorine and then use pH to determine your total. This is the state of the art. These are brand new, and they're just now becoming available over the past year. And another set will be available probably over this next year. But these are no maintenance. Once a year you could replace them out or do some work on them, but these will work 24 hours a day, do total residual oxidant. Some of them even do pH connectivity and other things, but these are where you want to be going in your process treatments paradigms. If you want to have a robust sensor that is really reliable, I've put them to use over the past couple of years, this particular one, and it is impressive, but they're not widely available yet. Yeah, way back there.
Do those have like an EPA standard to where we could use them for drinking water yet?
Yes, there is an EPA standard for solid state amperometric, there is.
And they're approved for water and wastewater treatment, or
I think they are, but I don't recall precisely, but I have a hunch this one is by Halogen Systems. I think it is. I think right now it finally is, because it's been available for about 4 years. And I think they have all their dots dotted and T's crossed, and I think they have an EPA method. There is an EPA method specifically for solid state amperometric now.
What's the name of the company that sells them?
This one's called Halogen Systems. It's based in Incline Village, Nevada. There's another company who does not have their act together. It is actually based in Laramie called Lucid Water. They have another one as well.
So does Hawk have something similar to it, or is this
No.
the ones?
Hawk has stayed away from them on the solid state. They are so entrenched in the CLD17s, you won't get them into this. Now they are watching these two companies carefully. So my guess is once their market penetration starts rising, Hawk will buy one and Watts Water will buy the other, if you will, because these will completely eliminate all online DPD analyzers. And these were developed using Navy funds. So all of this was developed. I was the original research scientist that developed this for the Navy, and invited both of these companies to get into the competing bids on it. But I developed the original technology for the Navy, working out of Laramie as a contractor for the Navy for 6 years, to measure total residual chlorine in a marine environment, which is totally out of control. So these are really good, and they get rid of all your headaches associated with DPD. And then on-site generation, let me just skip ahead to the climax here and right here. The green dots are good, the red dots are bad, and this is why you would want to go into on-site generation using salt. You don't have any hazardous materials to be dealing with, you don't have reactive materials, you don't have risks of human exposure, you don't have poison risks, you don't have right now, the uncertainty and risks associated with costs and transportation, storage and handling is driving people nuts, because the people who are staunch believers in liquid chlorine generation, now they're paying surcharges. I've seen contracts as high as over $3 a gallon per bleach, where it was only a year and a half ago, 57 cents. And right now we think the bleach prices can reach, we've seen places as high as $10, depending on how remote they are for transportation
Talked to
costs.
somebody yesterday that
Right. I'm dealing a lot in the Philippines. In the Philippines, we have systems down there we're working on, and their cost of bleach went through the roof. Because not only do they have to have a manufacturer on an island, they got to transport it by truck, then onto a boat, and then to another place. By the time they manufacture 12.5%, they're getting it on site at 5.
Wow.
And when you start adding that increased cost and that increased weight, their bleach costs effectively are now in the $6 a gallon range. And so now what used to be $1 million or $2 million capital cost with a 4-year payback, the capital cost payback is less than 18 months. So right now we're queuing up for a very nice 2024 rate, or 2023 right now. Because our cell costs, we've been able to control that. But at any rate, the on-site generation is the least problematic of all your generations if all you have to do is transport salt and have electricity. And then if you just look at these cute little pictograms, I like the on-site generation on the bottom right there. Nice little hollow circle. You know, there's nothing in there to worry about. Everything else is hazardous. What's worse with chlorine dioxide is it's hazardous from the beginning to the end. But it has a different approach, though. That's why you don't hear me nitpicking it. It's a different approach of treating because of its different kind of chemistry. So key features of on-site generation is, for one thing, for the electrical core systems versus what's already out there, we have PID control and on-off control. So you can batch or you can just dial it in. Your system can automatically read your distribution points and increase the current loads and change the water flows. We also have a boost mode. So if you don't mind throwing more salt at the problem temporarily, we have to detune all of our systems to do high output mode, 0.4%, to get the same salt use. So a lot of the parameters municipal water treaters use is how many pounds of salt per pounds a kilogram. We match that. But the problem is, the difference is in matching that is we just run a lower concentration, so we use more water. So you're treating with a little bit more water, but the water is not a cost commodity in the case of municipal water treatment. But either way, we derate our performance to do the 0.4% from doing, because we'll use 15 part per thousand salt. Our competitors use 30 part per thousand salt. So use twice the salt, twice the output, twice the heat, the real heavy thermal loads. We just keep our systems running at a very comfortable, reliable performance by running a lot lower salinity at half the output. Half salinity, half the output, the same salt consumption. But if you add salt to our systems, and match their salinity, our output goes up 30%, and we can actually increase the performance of that system temporarily to meet a surge demand. So the salt will average itself out as long as the salt doesn't exceeds your targets for salinity in the distribution chain. For that moment of doing a surge, our systems have a built-in boost mode, turbo mode, if you will, because that's our marine environment. That's our normal everyday operating criteria. And that is a differentiator. So we're differentiating ourselves by, one, running ourselves in the mode that we've designed for marine, long duty, harsh duty, and isolation locations in the world. We run them at lower salinity to meet your municipal market with the same salt consumption and a little bit lower power consumption. Okay, but we just run more water through it. But we give you a more stable product, and our product can then be PID controlled. You don't have to store all that water if you can run PID controlled. You can store all the water you want and turn it on full power off, full power on, full power off, or you just run it to whatever power demand you need. So it's a different paradigm because we come from a different market. And then we have all these other parameters going down here: lower concentration output, lower, more energy efficiency. Our cells are designed for harsh duty. Our cylindrical cells are more robust. Our wetted materials are very narrow, and we're in NSF approval right now. We expect to be approved by the end of this year. It's a long process, but our commercially pure titanium and our coatings are different than anybody else's, and we use CPVC and other NSF approved materials. So we are not seeing any issues so far with the NSF approval process to being completed by the end of the year. And our systems, because of the way we also design them, they're not very tall. We don't use passive hydrogen venting that require huge stacks that go up 10, 20 feet above your chlorinators. We can degas in the final tank. We just degas at the very end. In your final distribution tank, there's a degas tank, and then you dose. No need for degassing in your plant, inside if it's in a tank. So there's a history.
You're degassing at the generation site.
We still degas right at the exit tank, what's called the final tank, before you do your distribution dosing.
So after you went ahead and added the salt and electricity, it's going into a tank at a known dose, and that's where it's off gas.
Yes, correct. The final distribution point. So we've been in business 21 years. We're in 15 countries. We have a proprietary patented cell. We're ISO 9001. We're marine certified in Laramie, Wyoming. And we have systems that go anywhere from 10 to 4,000 pounds per day. We're made in America. Better yet, we are made in Wyoming, and we do brag about that when we're in foreign countries. One of the reasons we brag about that is they want to know where we are. We say we are central to all the U.S. ports. We're not isolated in the middle of nowhere. We are central to all the ports in the country. That is the story we tell. So we've been around, and that's just where we are. And I think I'll leave it at that. Do you have any questions? Shoot. Yeah.
What are the odds of setting up a tour so water systems could come see your technology?
We love giving tours. You can set up a tour anytime you want. You will get a long tour, and you will go as deep as you want. Gabe is back there with you. We love tours. We have given tours to all kinds. We have people all over the world to come to do FATs, factory acceptance tests, at our site. We take them out shooting and have burgers afterwards. They always take that over going to a formal dinner. They always go shooting and have burgers. It's a winner every time. But we love tours, and you're welcome. Anybody can come.
Sodium hypochlorite degrades.
Yes.
And that's one question as a chemist I'm curious. Do you know how, in layman's terms, when you get fresh 12.5%, how much does it degrade each week,
Okay.
roughly? Do you
I
know?
can give you a paper. Yes, I actually
Okay,
do
that
know.
would be,
And there's actually a paper on it.
okay,
So it's extremely temperature dependent.
okay,
So if you're at 70 degrees C versus 70 degrees Fahrenheit versus 80 degrees Fahrenheit, it's a big change. But I have a logarithmic chart that talks about concentration, temperature, and your half-life. So there's an actual curve set up that was developed and published by one of the big manufacturers back in the 60s. Hard paper to find, because you can only download the actual scanned-in copy. I will be glad to give you a copy of that.
I will get that.
Okay.
Now, along that same line, the hypochlorous acid, how does it degrade at the same as sodium hypochlorite or different?
So It's yes and no. So hypochlorous acid by definition is going to be at a lower pH, and so it's going to have a faster degradation curve. However, taking sodium hypochlorite and lowering its pH makes hypochlorous acid. So the same chart actually talks about both of those. And yes, the degradation rate is faster for hypochlorous acid, but the applications for hypochlorous acid are at orders of magnitude lower concentration. So when we make a batch of hypochlorous acid, say at about 190 parts per million at pH 6.5, we find that it lasts about 6 to 9 months in Laramie storage conditions inside a normal building. So a building that's right around 60 degrees Fahrenheit. Actually exceeds a lot of parameters you would have expected on the charts, but it does last a long time. You take concentrated bleach, it's stored in the same conditions, the half-life is probably about a year. So you should expect it to last about a year, 60 degrees C, sometimes even longer, but it all depends on the pH. So if the temperature's higher, the pH has to be higher. So it's this game of pH and temperature and concentration. So there's 3 parameters that affect your half-life. And it's all mapped out by this really cool study that was done by I think Allied Chemical or somebody a long time ago. I found that paper and I keep it on my hard disk and on my tablet and everything, because when I go into a ship and they say we've been storing it in an uncoated metal container for 3 weeks at 100 degrees Fahrenheit, I look at my chart and I go, I think it's about 1% right now. And they're like, no, we just bought it. And I'm like, no, it's 1%. And I go measure it, I'm like, oh, it's worse, it's 0.3. And they wasted all that money. But that's a very good question, and I do have the paper for you. It was hard when I
Take a
found
copy
it.
of that paper too, or a link, wherever it's at. I'd like to have that too.
Oh, sure. I think the link, I copied the link to the, I think I edited the PDF and put the link in the PDF once I found it. But I've relied on that curve a lot, and that curve has been pretty accurate. But it's orders of magnitude. I mean, you're talking, it's a logarithmic plot, and some half-lives can be long, some half-lives can be literally a day. Yes, but it varies tremendously. And the guarantees on most bulk chemical deliveries are 10%. That's the guarantee. So when I was over at Cheyenne, I was at the Weiss Water Treatment Plant a few weeks ago. They said they were getting it at 10%. That was their guarantee, and I measured it. The current batch that was a month old was actually right at 10%, but what disappointingly for me was the batch that was a year old was still at 9.5%. So I wasn't selling too good on that on-site generation, because they have good, cool storage and dark room, cool environment, and sure enough, and it's all plastic containers, no metal contact. So they're storing it correctly. So they're actually doing a very good job of meeting the half-life requirements. It was disappointing from trying to sell the benefits of an on-site generator though. But we're going to still do a pilot over at the water reuse facility at Cheyenne, and we're in the process of working with the engineering firm to bid the system for the Sherrard water treatment. If you've heard that they've built in their own power generator. They're using the elevation change of their reservoir to do power generation, which means now they can actually put an on-site generator. What was funny was they actually planned to do liquid bleach as their temporary, switching out from gas to liquid to on-site generation. I said, well, we have a trailer that we could drive right up that could generate their entire demand on-site. They could actually go on-site using our trailer, which is designed for emergency response, that we could generate the entire needs for their plant at 52 million gallons a day with this 28-foot trailer. That's on wheels. Just drive it right up and put a salt tank beside it and generate. So now I think they're changing the paradigm on their intermediate options as well. They don't have to go buy bulk chemical, because that's crazy expensive. Yeah.
So, just thinking like, if there was an emergency in the state, you guys can run off your basic gen set on a boat. So I'm wondering if we could get like Homeland Security to buy an on-site generator that could be moved to a facility if we had, if somebody lost their treatment.
That is, so in Florida, they just had the hurricane, and in Florida we presented to them about emergency response for not only having on-site hypochlorite generation for sodium hypochlorite, but to also, it leads to the hypochlorous acid, which means it can do wound care, sanitation, potable water. So it is a logical thing that we have this generator that can generate, it can replace, the generator we have on wheels right now can replace 600 gallons of 12% bleach per day.
But when you're doing that, in this portable unit or emergency unit, how are you transporting the salt?
That comes in a separate truck. So we have a van trailer that shows up with salt.
So regardless, portable or not, you're going to have salt going wherever you're going.
Correct.
And
Now-
then this temporary unit has a storage bay on it, or you leave the truck with it and it,
We leave a truck, we bring a van truck with say 25 tons of salt, we leave it there.
and then does that salt get turned into a brine and then pumped through
Correct.
the electrical cells? So you have to be able to turn, so do you have to have, to make that brine, do you already need to have clean water?
You should start with groundwater, clean water, groundwater, yes, you're not
So you
starting with
have to
surface water.
have-
Any clean water source that could ultimately be rendered potable if you're doing a potable emergency.
Gotcha.
In the case of Florida, for disinfection, they can they can just put a hose right in the Gulf. And we don't even need to bring a briner. They can literally make sanitation, because the water coming in from the marine will be completely disinfected and dealgified through the chlorine, through our cells. It'll come out sanitized.
But you,
And so they can use that as sanitation right off the get-go. You actually drink sea salts or eat sea salts in your potato chips you buy, and salt you put on, right now, that, all you're doing is getting rid of the biology. But when you run it through our cells, it comes exposed to, you normally need to do 100% kill, a contact time of, 6 seconds at a ppm or something like that. It's only a few seconds, but now we're coming through our cells at 4,000 ppm, everything's dead.
but let's just say you're not dealing with salt, you're out here in this area, as the turbidity goes up, how is that going to affect the salt brine of whatever you're sending through the cell? The higher the turbidity should affect the outcome of the solution going through the electrical cells.
It has not in our marine environments, because we take raw seawater and all bed density conditions. We still get the same concentration coming through, and often water coming in black, brown, dark green comes out crystal clear. All of it is destroyed. I can show you a case study I did in Piney Point in a pH 3 water that was all eutrophied. We ran it through our cells and it came out with no smell. We ran it through at 2,000 parts per million. It came out odorless, ammonia free, and all the algae was destroyed, and it was crystal clear water.
So then, there would be a zero organics problem.
Basically, yes, we destroy all of it. At these concentrations, running through a cell does a lot to it, because you also remember the pH shifting. It's seeing pH zones through the cells hitting pH 10 and pH 1. We're not only acidifying and basifying it, but we're also chlorinating it and destroying it with the radicals.
The reason why I said organics is because I'm trying to think down the road with the time of the contact, we all have disinfection byproduct problems.
Sure.
In time, you would probably still have that with this, wouldn't you?
In the case of running clean water through our cells and then dosing it in like you would bleach, you will still end up with the same disinfectant byproduct path you would have, because at no point are you taking that bulk water and shoving all of it through our cells.
Yeah, and that's why I was just thinking so I'm back up to the portable unit. We all are trying to limit as many organics and turbidity or whatever we have coming in, so that way we don't
Correct.
have the organic problem at the end of the system. But that's just a little different dealing with the seawater. I mean, it's just another problem.
Correct.
It's a different animal.
They are, but the idea of having an emergency response system is straightforward. It's not a lot of capex. A generator, a salt supply, it's literally 3 trailers, and you could go service any plant in a matter of hours and recover whatever burst needs, emergency needs, or you would have, or if a plant went down, or a supply shortage. But it isn't it's very readily doable, and that is something we're trying to pitch, because our systems actually are very amenable to transportation, because we put them on boats and we ship them the vessels, and they literally cut the vessels, pop them in, turn them on, and we've had 0 failures of our chlorinators on any ship.
What, because the percentage is so much lower with the sodium hypochlorite that we use, the 12.5%, we're injecting a very small amount, so we're using peristaltic pumps.
Correct.
What are most of the systems that are using these? Are they using just a regular centrifugal pump to pump in the solution, basically?
So that's a good question. The Marlowe Watson pumps are using at at Crow Creek and Cheyenne. They can even though we're using technically 25 times more volume, their Marlowe Watson pumps can handle it. Because now we just go from 0.03 or something to 1.0, and their pump can actually handle that. They are so barely turning on their industrial peristaltic pumps, that those peristaltic pumps actually can handle the 1 GPM we're gonna shift it to without changing. It's not even at the full upper limit of those pumps. So depending on the size pumps you have, yes, you could use a normal turbine pump, you could use a diaphragm-based motorized pumps, or AOC pump, or AOD, aero diaphragm pumps. You can dose it many different ways, but it's still a very small, inexpensive pump, because you're really talking typically 1 to 5 gallons per minute. So it's still not very big. And I was at Blue and White's booth at WEFTEC 2 weeks ago, and they had some really nice double diaphragm electric drive pumps that would perfectly match what we're looking for. The built-in diagnostics, the PID control, again, because we can PID control our entire system. So we can dynamically change our flow rates and our currents to match whatever your needs are, and you could still always have an intermediate tank buffer that would be a 24-hour capacity. So you could keep that tank continuously flushing to whatever needs you need, but you don't need to go store excessive amounts or little amounts. In the case of the Sherrard water treatment plant and its new paradigm, they were speccing in a treatment paradigm of 52 million gallons a day, 24 hours, because of the harsh winters. Well, they hadn't considered the fact that in the harsh winters, they're only using 4 million gallons a day of water treatment. So all of a sudden, their treatment volumes, the storage volumes drop, and the fact that we use twice as much water is no longer an issue. It's not going from 20,000 gallons to 40,000 gallons of storage. It literally is just 5,000 to 10,000. So it's a normal single tank size. And they had plenty of space there to store as much water as they wanted, but we would run a flow through. Again, we're not going to degrade as fast. So in that time of storage at 0.4%, we're going to degrade half the rate of the 0.8%. The 0.8 comes out at 30 degrees C. The 0.4 only comes out at 40 degrees C comes out at 0.8. We come out around 30 degrees C or less. So that temperature change is going to have an order of magnitude effect, a logarithmic effect on the stability from the time it goes through storage to dosing. So, sorry, go up front here.
So I actually work out at Sherrard, and we have OSG over at Round Top for our wells, and then we
Yeah.
have one down at Swan Ranch. And it's the microfloor. What's the difference between your system and the microfloor?
Our cells are different. The biggest difference is we're not going to generate you turn those on like a few hours a day, I think, and then you
Right.
store in big tanks, and that
Yes.
water is very hot,
Right.
and you're 0.8%, and you see a lot of scaling in your tanks.
Yes.
We're going to be a lot colder, lower concentration, so you're going to dose twice as much water through them. So your
Okay.
dosing pumps will run very healthy, and you should see a lot less fallout and precipitation in your tanks, because the lower temperature and the lower concentration is going to be not as harsh. We will use the same amount of salt though, and you'll
Okay.
just run more water through your system.
So with the degradation of the solution, because like we constantly have to check to see what the percentage is on it, and it fluctuates a lot because of the storage tanks out there around
Right.
Round Top. Is it gonna be as all over the board as far as the
We would expect it to
solution
be
is
very
concerned?
stable. We would, not having yet installed the first,
Right.
we're still trying to get our first installation on the municipal water side. We expect it to be pretty predictable and stable.
Okay, so it won't be as big of a
We
fluctuation
would not
as
expect
the
that.
microfloor that we got now.
Correct. And that is due to the hydraulic dynamics of our cells. The cells are running under steady state, steady conditions with complete flushing of all the electrode areas at all times. Our water temperatures are predictable, our currents are predictable, everything is controlled. When you do parallel plates, there's a whole lot of, looked at some of those cells.
It's terrible, yeah.
Right,
it
and that's where
affects everything.
that's where the problem is happening.
Right.
It's the fact that your water dynamics between any set of plates that are creating the sodium hypochlorite is out of control. You've got hot spots, cold spots, dead spots.
And we have lots of TDS in those wells over there too.
None of that will affect our cells, because we work in the highest TDS environment there is, open
Right.
seawater, and coastal seawater. So we don't expect any of those issues to affect us with brine. We're looking at the most pleasant environment ever when you're dealing with a salt saturator, and diluting that down with what would be very low scale water, low hardness water. We expect that to be entirely different, and that's why we're excited to do the pilot
Right.
over at Crow Creek. Unfortunately, until we got all the legal stuff done,
Right.
the season was over. Now they're like, come back in April. We're not running over the winter, so it's a drag, but we'll get there. We have the system all built and ready to go. We just didn't have it, so we have another place.
The
we're
red
working.
tape.
Red tape. Took a long time to get through the red tape. But we do expect a huge difference, and we're willing to stand behind that difference, because We don't have insecurities in the way our cells operate.
I was just wondering, as an operator, you know, how we were gonna approach that every day.
It really, the way our systems run is they monitor the current. You can put online analyzer, but we just monitor the current on the cells, and you know exactly what you're generating. So you just change the current to match your water flow rates. And when we're doing this in the big, with our seawater systems and all the power plants, gravimetrically, all of our work is done gravimetrically. We don't need sensors to do any of our work. It's just current proportional drive to water flow rates, to demand. And that's how they've run for decades. Surprisingly, if you do it right, it is that simple. Part of the problems with pushing 0.8 is the highest theoretical limit you can get out of an open cell design for municipal water treatment is just close to 1%. It's usually right around 0.8 to 0.85. But you'll find that they usually never hit those targets because it's so hard to do and it's very stressful in the water. You're heating the water up like crazy because the water is electrically conductive, and that creates an immediate decomposition coming right out of the end goal. And so that is an unstable system, the way they do their feedback loops and everything. They have you go through one cell, part of it comes back through the first cell, go through the third cell, part of it's coming back through. You don't have control of that. We are a one pass, water in, water out. It is the same water 24 hours a day coming out of that we programmed it to do. There is no out of control feedback loops. There are no arts. So we've done the best we could to take electrochemistry and turn it into an engineering science. Because water comes in, goes out at the end, always, predictably, reliably, the same thermodynamics, every single time. That's why we were unwilling, when we started going down the path of going into the municipal market, to say, wow, we're just gonna succumb to the same pressures, everybody does 0.8, we're gonna do 0.8. And when we started looking at it, we're like, we're gonna have the same problems they do. And now we take a system that's got a high reliable credibility in the marine market, and we've just detuned it and made it a fluster and a control nightmare. Why would we do that? So the question is, does it bother you to use twice as much water for the same salt consumption? If so, well, buy the competitors. But if you don't, and you can live with the water that you're using to go simply on the side loop to chlorinate, then we're going to be a better system. That's the model, and we cannot see anything wrong with that model, because that is what we're doing. And so we're running this pilot. If you come down to Laramie soon, you'll see the trailer there running right now. Because soon it's going to go to Florida, where it's going to be going to the city of Haines City outside of Orlando, somewhere. We're going to take over their entire treatment plant. They're doing 1,200 gallons of bleach a day, and we're going to do a 2-week pilot there, and then they're going to buy a system, they say. And maybe they'll buy the trailer. That'd be.
So potentially you're saying that there's no scaling and as operators, you're not having to maintain constantly like on the microfloor?
There's nothing for you to do because the system maintains itself. We're current driven, so we drive the current to match your productive water needs. So you would drive the current based on millions of gallons of water per day.
Right.
The voltage and the scaling all takes care of itself. When it hits a certain point and it's time to do an acid wash, which is why we do say 3 flow trains, 3 by 50%. You can shut one down, do the acid wash. We don't think that's going to be more than a couple times a year.
Right, okay.
Then you
That's
can
what I was
do,
wondering.
not very often. In the marine environment, the heaviest environment in the world is every 400 hours, once a week.
Wow.
So you're talking in orders of magnitude reduction in scale, especially if you even soften the water. So we're expecting this to be very infrequent, very, very infrequent. But it's automatic. The scale and the system adjusts itself. This is what confuses me when you talk about all these controls you worry about, because our systems never had that. Our systems are drive the current, the voltage floats, and then when the voltage exceeds a certain point, you'll get the warnings that it's time to do an acid wash because your cells have accumulated. And in the Philippines or in the Southeast Asian countries, we will run high Reynolds numbers to shake that off. But that creates in their case, it creates a waste stream, but that just goes right back to their cooling towers. They don't care. And in municipal water, you don't want a waste stream. So in which case we would do an acid wash with muriatic acid neutralized with sodium bicarbonate or something. You still have no waste stream because all of that was NSF approved materials. So you end up putting more salt, a little bit of extra salt down the line.
It's exciting.
So technically you should have no waste stream, anything we're doing. And even our hypochlorous acid generator model we designed that the EPA looked at, we have no waste stream. We don't have a cathodic fluid and an anionic fluid, and then have to waste this cathodic fluid as some kind of a cleaner. We actually, 100% of the water and salt in and the muriatic acid in ends up in product. No waste streams. Again, we've designed everything we've done. Again, we have, I think, 5 graduates from the University of Wyoming working for us now. 2 chemical engineers. Gabe's one of the guys, he's in construction management, but he loves the chemistry. We've got mechanical engineers, and they have learned all of this over the past 4 years. And now they're running all the research, all the development, and they see it and they get it, and we're doing really good work.
So, figure out a way for me to, collect the rejection salts from reverse osmosis.
We can do that. So we already do that in Florida. We're going down to do this pilot, as I mentioned, at Haines City. We're going to use RO rejection water from a company called Allied Chemical, and we're going to run entirely on salt reject from an RO plant.
Wow.
And all of it is already potable water RO reject, and it's going to run the whole system.
Well, I'll tell you what, then, get the guns and the ammo together, and if you prefer barbecues, Michelle sets up the tour, we'll be down.
Yeah, we can do reject. We just look at the certificates and the water quality things, not a problem. On that water, we're doing a 12-to-1. For every gallon of that brine we get 12 gallons of source brine into our system. So it's really efficient use of it.
Does it matter what's in the brine? Because some of our, in Wyoming, we don't worry about brackish water so much as we worry about nitrates and uranium. Those are the big two reasons why we have our own ones in the state.
I would worry about fluoride.
Fluoride.
Fluoride will attack the anionic coating, so it will greatly reduce your cell life. But we can compensate for that through cost of the coating or coating refurbishing plant. But fluoride is our only enemy of everything you just mentioned there.
We pull out about 2 parts per million.
Fluoride, we normally are fine. We design the cells to handle up to 1. So we would probably, that in effect is gonna be like a cold water coating. It's gonna be a lot of scavenging, reactive fluoride, fluoroxides. So we would actually have to put more coating on to maintain the same warranty. So the cells would cost more, or we just replace your cells more frequently on a different cycle. But the anodes can all be refurbished. And we do all that in Wyoming. Our weld shop, just so you know, is in Sheridan. All of our plate rolling and all of our titanium is inventoried in Sheridan. All of our steel work is done in Sheridan. All of our coatings are done in Casper. And then all of our final assembly and manufacturing and testing is done in Laramie. So we run straight down from north to south.
Who's welding for you?
Wyoming Welding Machine, Daniel Jolman, a young gentleman who was laid off from Emmett Technologies about 5 years ago, came down to Laramie, showed me that he could do welding and he wanted to do titanium very badly. So we trained him up a little bit and he didn't need any further than that. Now he's got our plate roll, he's got his own laser cutters, he's got his own brake presses, he's got his own shop right by the airport, right next to a company called Craftco. And so we run everything through him because if we have so much as a pinhole leak in an electrical chemical cell that we bring down and do hydro testing on, he is there the next morning. He wanted to do all the hydro testing in Sheridan. I'm like, no, we have to maintain ISO and quality control in Laramie. I said, either you get your welding right, that you're not coming down, or you told me you were good enough to do welding. I said, there should be no problem in me doing the hydro testing in Laramie. Well, he does a little bit of hydro testing. We do the final testing. He's only in 5 years, in like 150 cells, he's only had 1 pinhole.
Wow.
But he will be down the next morning. As long as it takes for him to hop in his truck and drive down, I can wait that long. We don't have any issues. And I will drive up to his shop on a regular basis just to chat, and we run our own trucks and trailers back and forth, moving the materials back and forth. And it's great because it's part of the family, if you will. And the same with our paint guy, because he'll move stuff down in bulk to the paint booth. He's got 17 acres. While he's coating, he's already got all of our aluminum and stainless and titanium work there. We'll drive up and fetch it, or if the weathers are bad, they'll drive it down. But we work together, the 3 shops. So our shop, the paint booth called Mark's Body and Fab out by the airport here in Casper. And then Sheridan, so between these 3 sites, we move materials and we don't let winter ever get in our ways to meet deliveries for any international shipment. We've never missed a schedule. So again, come down to Laramie, see us, call me, or any, we got Mark Pierce, right? Pierce, sorry. I got it before I am, that's where I'm tired. Mark is here, Gabe is here, Darwin was here earlier in the week, he left today, or yesterday, I think. And I'm here today, but we certainly love tours, show you the cells, show you what we do, but again, we're different. We're doing it our way, we're doing it in Wyoming.
So I saw something in one of our study books about they were looking to utilize the salts from the desalinization plants for sodium hypochlorite. Do you know anything about that?
Who, here or?
No, on the coasts.
That would be perfectly fine. Now, the salts with seawater for desal plants using it for potable water would be another problem because you don't have NSF approved seawater salts typically for potable water.
Good, 'cause-
So it is possible, but I don't think they would spend the money segregating the salt out to make it pure sodium chloride.
So it wouldn't be economically
I
feasible.
think it could create a problem. For wastewater treatment, that's not water reuse, not a problem.
That would work.
That would be
Yeah.
perfectly fine. You know, but in Cheyenne, you want to put your water reuse back into lakes, and you want to keep those lakes fresh water. You want
Right.
to keep the same organisms growing healthily, so we wouldn't want to use seawater because you would change the ionic balance substantially, especially the bromines. In marine water, you have a lot of bromine to deal with, and that would be a no-no in the human contact, human exposure water side. So.
What's it take for, or what's it cost for you guys to come and look at a system to see what rough costs would be to have something of what you guys have installed?
We do that for free or preferably for a lunch. You know, you entice us with food, we will gladly come out, I will come out and train with my guys, and I'm still training them, so I like to come out along and make sure, and we work it together, but we enjoy doing that because our beachhead, if you, so to speak, since we're in the marine market, our beachhead here is the state of Wyoming. We want to get into the state of Wyoming heavily because we can support it, it's in our backyard. If we're going to inadvertently make a mistake, I'd rather do it here because I can hop in my truck and come over and visit it. But we don't have a history of making mistakes. You know, we don't fly all over the world to support our systems. We're always available 24 hours a day on the ship support side, but everything that breaks is a pump or a valve or something that they said they didn't muck with it, but they did muck with it. I wish we could charge them twice as much, you know. So, you know, they're always tampering with it. We always find it in their logs what they tampered with. But the things that fail are your conventional failure points. Is just typically filter, well, we use strainers, we don't even require filters upstream of our cells. Our cell gap's wider than these competitive technologies. We can swallow large stuff through our cells. We just require strainers, not filters. So we don't have a whole lot of maintenance, but just your conventional stuff's fail. Your dosing pumps, you know, your plumbing could crack or something like that. But the electrochemical part, the rectifier parts are extremely robust, and we've gone out of our way to certify those. But we'll be glad to come to a site and look at what you got, and I wrote up this very fancy calculator tool that takes your application needs and spits out approximate orders of magnitudes of what it will cost to put in a system, and then we work through any variances and differences, because everybody's end goal has got some variances in it, and that's the part I thrive on. What are the changes and what are the other angles we can look at how you treat your water to make sure we get what you need and get it in a way that provides the stability, the redundancy, or whatever applications you want, and we just go through it with you. So glad to do it. Just give us a shout. We will come visit. Gabe's right there beside you. We'll come up. All right, so I went off script quite a bit here, but I was hopefully giving you something worth your CEC credits, some science, some chemistry, and an impartial, try to be impartial. I'm first and foremost, I'm an engineering scientist, so I look for the truth in everything we do. So if you have a water problem of any kind, I enjoy getting involved with it, from the biology side of it the whole way through the physics of it. So thank you for your time.
Thank you.
Thank you.
I'm excited.